Temperature dependence of the electrical resistivity of a metal. The electrical resistivity ρ of a metal is proportional to probability that an electron is scattered by the vibrating atoms in the lattice. And this probability is in turn proportional to the mean square amplitude of vibration of these atoms. How does the electrical resistivity of the metal depend on its absolute temperature in the range near room temperature or above, where classical statistical mechanics can validly be applied to discuss the vibrations of the atoms in the metal? So we're not talking about a quantum harmonic oscillator, we have a classical harmonic oscillator. For the classical harmonic oscillator, we can write the total energy of a harmonic oscillator to be 1 over 2 kx squared, where k is our spring constant, plus 1 over 2 mv squared, and the total energy must be conserved, so it should be equal to 1 over 2 ka squared, where a is the amplitude of the oscillations. So k is the spring constant. In the case of atoms in a solid, this would be related to the bond strength, and a is the amplitude of the oscillations, x is basically displacement from equilibrium, and v is the velocity. So if I use the equipartition theorem, if I take the average value of these, I will find, using equipartition theorem, I will find that the mean energy per oscillator will be equal to 1 over 2 kT plus 1 over 2 kT, where k is now the Boltzmann constant. So this k is Boltzmann constant, not the spring constant. So we have two different k's. So let's use different colors. This is the spring constant, k, and this is the Boltzmann constant, k, which is in the thermal energy. Okay, so therefore we find that the mean energy per oscillator will be equal to kT, which is the mean value of, so this k is our Boltzmann constant, which is the mean value of 1 over 2 k spring constant amplitude squared. So if I take the mean value so that basically mean value of amplitude squared. So this is basically telling me that the mean value of the amplitude squared is Boltzmann constant k times temperature divided by multiplied by 2 divided by the spring constant k. So these k's don't cancel because they're different k's. Okay, so basically, since I have the probability of scattering is proportional to amplitude squared, we find that the resistivity is linearly dependent on temperature, because mean value of amplitude squared varies with temperature. It's linearly dependent on temperature. Therefore, the classical statistical mechanics tells me in this temperature range, the resistivity is ρ is a linearly increasing function of the absolute temperature T. Okay, so we're discussing temperature dependence of the electrical resistivity of a metal. It is at room temperature, it is dominated by the scattering of electrons from vibrating atoms in the lattice, and we can treat the vibrations as classical vibrations here. So a classical harmonic oscillator has energy 1/2 kx squared plus 1/2 mv squared, where x is the displacement from equilibrium, k is the spring constant, m is the mass of the atom that is oscillating, and A is the amplitude. So using equipartition theorem for each independent degree of freedom x and v, here I have 1/2 kT contribution. So kT is the mean energy per oscillator, which is the mean value of 1/2 k amplitude squared. So this k is the spring constant, the kT, k in kT is the Boltzmann constant. So amplitude squared average value is 2 kT, 2 thermal energy divided by the spring constant, and I can see that the amplitude squared is average value is proportional to T. Therefore the resistivity, which is determined by the probability of scattering, is linearly increasing function of temperature.